Hello and welcome everyone to this year's Cloud Foundry Summit, the virtual one. My name is Matthias. I'm ambassador for Cloud Foundry and also the organizer of a meetup in Stuttgart. And today I'm going to give a talk about containers. So I'm just going to share my screen real quick. And I hope you can all see this slide deck now. So yeah, as I said, this is about various options. In a situation, a lot of us will know from the development world on how to get from your source code to a container image. Now, as this might sound straightforward to some of you might not be aware that there are a couple of different options to do so. And today we're going to look at some of them and I give a few details about it. So 50 minutes is not really long. That's why I probably skip the demo part and dive into that straight. Now, before we talk about what is the best options for container images, for building them, we should probably have a look what container images really are. So this is an entry-level talk, so a bit of information around that. As we probably all know, containers are isolated processes in a certain environment that bring along all their process libraries and dependencies. And an image is basically a template to instantiate those containers. Now, in this chart, you can see a bit of an example on how to create an image that runs a Java application. So from a container image, you would execute a run command. Then you get a running container where you can install your Java. Then again, you can commit this to an image, run it again, copy the application inside, and then commit it again. So the importance of this slide is basically to see that those containers are built in this kind of layered architecture. And this layered architecture is one thing you can look at to optimize when you want to improve your builds. Now, as this progress we've just seen with the repeating run and commit commands was a bit cumbersome, Docker very soon realized that and came up with the idea of kind of a so-called Dockerfile. This was in May 2013, about 2 months after Docker was born. So you could potentially say it was there from all the beginning. Now, how does this work? The basic idea is that it is being processed like kind of a batch file. So like one step executed after the other, where in the beginning you specify a so-called base image, and then you run all those commands. So this would be an equivalent to the one I've shown you before. Now, if you do it that way, you're basically under full control on defining what is your image. In this case, I'm building a Java application, so I can define what is my Java runtime, copy my code in there, and so on. However, there are already predefined images available for you, so you could save the initial step and already start with a predefined Java image. Now, the problem here is there are quite a few. And the problem you can run into is basically say, which is the right image for me, or who would I trust as an image provider? Now, if you look a little bit on how you would actually use those images, in the end, this containerizing step is a step of standardization for your application workload. And it very often happens that you use it as part of a pipeline where you code, build, containerize, and deploy your application. Now, the standard scope of a Dockerfile is basically the one to containerize the code artifact. However, as most of those steps are also meant to be a standardization kind of flow, you could potentially imagine of extending the scope of the Dockerfile for building and containerizing your application. Now, Docker also has come up with a solution for that, which is called the multi-stage Dockerfile. In this one, you can separate your image process into stages and say, well, I use this file only for building my application with a predefined environment like a Maven JDK combination. And then you have a separate stage in that file where you basically start from scratch with a new image and copy the result of the previous build stage. And this way you can really separate the two different steps completely from each other. And in the end, you come up with a fairly clean image that contains your code that you have done in a standardized build step just before. So the Docker file evolution kind of continued with the step called build kit, which has become available starting from 2018, promising a lot of cool things, like what makes images really good is like if they're small, fast to build, good caching, good security, and so on. So BuildKit claims to do quite a few of those. For example, if you have more than the two stages that I had shown you before, like in this pseudocode, that you have a stage for like building your base Java container and you're building your base Gradle container, if you don't try the originator of those and then use them later on, then Docker could potentially detect that and run those stages in parallel and hence again optimize more for your time. Another cool thing is that it allows so-called experimental images to be used. For example, this one, which allows you to cache a certain step and read or write contents to the file system outside of your container. This wasn't possible before. And if you have ever built an application in Java with Maven or with Node and NPM, you know that running this in a container gives you always the feeling as you would download half of the internet. So especially in development environments, this might come in quite handy, as you can like kind of outsource all those previously downloaded jar files and then improve the timing in that. So from that evolution of Dockerfiles, you can see quite a bit what are the certain aspects Docker tried to improve and makes an image process better, or what does make a container image good. In the end, there's a couple of things, like as I said before, speed, both in terms of building and in terms of loading, then the size of the image, structure, standardization, you could potentially say security as well. And if you want to try to optimize your image build, these are probably factors to look out for. Now, what I see, however, very often is that people try to optimize for speed and size without looking at the details much. Now, if you look at an image, as I said before, it consists of layers, where on the bottom you have base operating system, then dependencies on top, and then most likely your application on the top level. However, like the overall size is, of course, the sum of all the parts inside. Now, the stuff on the bottom normally doesn't change so often. So if you have to exchange your base OS layer with every image build, I would say you're doing something wrong. But your application layer will probably change very often. And if you do that, if you optimize in that space, because that is constantly reloaded, you gain much more efficiency than optimizing here on the bottom. Now, next to Docker, there is more. I mean, this is the Cloud Foundry Summit. Of course, we should mention some things called Buildpacks. This is something that Heroku initially initiated, and that a colleague of mine from a company called Codecentric put into a great blog post, and this is where I took the chart from. He kind of put the Buildpacks into a relation with the Docker releases when Heroku played a role, Cloud Foundry, and nowadays with the Cloud-Native Buildpacks as a CNCF project. Also, we will look a little bit at Chip, at technology from Google to build containers. And there were others influencing the flow as well. For example, the Spotify Docker Maven plugin, which was like the first one to enable Maven to build a container image after the build step. Now, Chip works pretty much exactly like that. It comes as a Maven or Gradle plugin. And when you build your Java application, then you can just invoke that plugin, and out of the step doesn't only come a Java executable, but like something packaged into a container. You can run this, of course, on your local operating system. And the important fact here is really that it doesn't require a Docker daemon to be run. So you build that image without the help of a Docker daemon. And this can then be exported into like container registry, like the Docker Hub. You can build it to a local Docker daemon, but you don't have to, or you can just export it as a tar file. Now, taking a step back, what we've just said about those layers and the parts where the image changes. Like in my very first examples, I always used a copy step to copy my application in here as one big chunk. Now, for Java, it is also true that this application also has an internal kind of structure where you have dependencies, resource files, and class files. And the same thing that applies for the overall container applies for the Java application too. So very often those dependency jars and resource files, they don't really change much. It's very often only that class files. And if you can narrow it down to that, you can, of course, improve the efficiency of your build much more. And Chip does exactly do that. So Chip only updates, like separates the 3 top layers of your container image into that. And if only the class files changes, only this part will be updated. Now, speaking a little bit about Buildpack before I finish, like for people not familiar with the concept, it works in a way coming from the original Heroku platform as a service idea to basically be able to detect what kind of code you're running and put a certain build pack underneath. And with that build pack, it will transform into like a runnable application. Later on, this was called container then. And this idea was taken by Foundry and also continued with Heroku and came together again as the Cloud-Native Buildpacks project. One of an implementation of this build pack, so-called kind of definition, is Paketo, one we will look into in a second. Now, how those build packs work in general is, in this case, you really need a Docker daemon because you run a so-called CLI command called pack that will download the builder image. This is basically your implementation of the specification. So Paketo will download another builder image than, for example, a Google implementation. And within that build pack, all that stuff happens, like detecting the runtime, choosing the appropriate build pack, and then come up with some application image that has been built out of that. And depending on the way the build packs are structured and the efficient they are, this is basically how it results in your final image. Now, and one additional thing that this technology provides is not only updating, like building the image and changing things on the top, but it also can update the base image while the other parts keep the same. Now that I told you before, it's more likely that the top parts change. This is of course true, but of course there could also be a situation where your top parts are absolutely fine and you need to update the base image, for example, because it has a detected vulnerability or so. We will see that in the Paketo example here. So Paketo is a technology, it's like an implementation of this build pack specification that comes straight out of Foundry and uses like all the build pack experience from Foundry. So you have quite a set of runtime and language support here. And now if you imagine you have a lot of different microservices packaged into containers with a lot of different languages and runtimes, but they all share the common base image. And you have to patch those, or something might come up and that you know you need to patch them, then you can quickly say, well, I'm affected or I'm not affected. And if I'm affected, then the build pack will just automatically update all of them. So you could rebase them and get them running into production a lot quicker again without having to evaluate, is this image affected or this one? This is a situation that you might most likely end up with if you have various Docker files built by various people. Now, as I said, in this case, you would only have to take that step and apply it across the board of all your container images. The flow of this one is exactly the same. It downloads the Paketo builder image and then runs the build execution. You come out with the application image. And in the special case of Java, it works in a very similar way as Paketo, where it also differentiates into class, resource, and dependency jars. So in an ideal case, only this top layer will have to be updated. In case if you happen to have a Spring Boot application, this also works as a Maven plugin. So you don't really have to invoke the pack command. You can just attach it to Maven or Gradle. And then similar as to Chip or that Spotify plugin, this will come out with an image, but it will use the Buildpack technology and download the Paketo builder image and run through all that. So in this case, you kind of have an option which way you want to continue. Now, as I guess I'm running out of time, yeah, so of course, when deciding on which build option to take, it is of course always relevant to make yourself clear about who owns the image and who owns the build process. And do you as a developer really want to own an image where the base image is something you didn't contribute to, or where you don't know where it's coming from? And of course, using Dockerfiles gives you a lot more freedom and flexibility to pick and choose the options you want to have. But in the end, it also makes you the owner of that. Whereas using something like Chip or Cloud-Native Buildpacks, you have a certain kind of source where these parts are coming from. And especially in the case of Cloud Foundry, those buildpacks have been maintained and used for quite a long time and are updated very frequently. So with that, I want to say thank you for listening. Normally, I do this presentation with a bit of code. So if you want to, you can check this repo for the code pieces and play through that yourself. All right. So thank you very much for listening. And I wish you a nice rest of the conference.
If you have any questions, feel free to post them. Oh, there is a question. Have you played with abstractions on top of build tooling that present more in no, thanks, Andrew. I don't have experience with that yet. I've played also with source to image from OpenShift, and this is basically what's my experience so far. So, but I'll take that with me, and I'll definitely extend the talk and add some new possibilities to that.